So looking at G prime here, the first, really the most obvious thing probably is the fact that it is differentiable because G prime is defined at A. All right, so we'll mark this one as true because, hey, there's a point here, so the derivative does exist and it's defined. It equals whatever that y value is, okay, at A. So now let's go back to this first one. How do we know it's continuous?
Because it's differentiable, so it's continuous.
Yes, okay, you guys remember we looked at that. If it's differentiable, we know it's automatically continuous. It doesn't necessarily work the other way around, okay? So we know this is true. Remember, here are all of our continuous functions. If we looked at this as a Venn diagram, and within all the continuous functions, these ones are differentiable. So if it's differentiable, it's automatically inside that set of continuous functions. All right? Yes?
Can you explain what's differentiable?
Differentiable means you are able to differentiate. In other words, you're able to take the derivative at that point. Yeah.
Okay.
No, that's okay. It's a weird kind of word. And here's the thing, we use differentiable, we say we take the derivative, we say we differentiate. All of those words are basically words that are saying the same thing, just slightly different ways. So it's hard to keep track of them sometimes. Okay, so now we know that this is either, well, actually, just by process of elimination, we know which choice it is. What does this have to be? E, all right? Because we know 1 and 2 work, and E is the only one that has 1 and 2. But E also says that 3 works. So how do we know that G is increasing?
Because the derivative is positive.
Very good, yeah. G prime is positive. Okay. So then we know it is increasing. This is one thing that's kind of challenging to accept sometimes because, you know, our brains want to just look at what we can see here and not think about the bigger picture. From here all the way as far as we can tell, G prime is greater than 0, which means G is increasing. And you might say, well, wait a sec, G prime is going downhill here. How is G increasing? Yes, it's going downhill. That just means that as we're increasing, we're not increasing quite as fast as it goes downhill. But we are still increasing until the point where it hits this. Then it starts to decrease once G prime gets into the negatives. Okay? So, there's a good warm-up for us. All right, so let's go ahead and get back to lesson 16 here. And we're going to look at 2 rules today for taking the derivative. All right? Now, if you recall that the derivative is just a limit, we had already defined one of the rules for derivatives when we were taking the derivative of a sum of multiple things based off of what we knew we were able to do with limits. We knew we were able to take the limit of a sum by taking the limit of one part and then the limit of the other term and then the limit of the other term for however many terms we had, and then add up all those limits. So we extended that to derivatives and said, okay, if we are taking the derivative of the sum of a bunch of terms, we can simply take the derivative of the first one, the derivative of the second, derivative of the third, and just add those derivatives together after we took the derivative. The product doesn't work that way. When we took the limit of a product, we couldn't just take each individual piece and take the limit of each factor and then multiply all those limits together. It didn't work that way. All right? So, because it wouldn't work for limits, it's not going to work for derivatives either. So we have to have another rule here. And this is what's known as our product rule. Now, you'll see people use a little different notation. Sometimes you'll see them use U and V instead of F and G. All right. Sometimes they'll reverse the order of this. For example, they might say F prime G plus FG prime. That's the way I learned it, but the way the text has it for us is F times G prime plus G times F prime. And the basic idea is this. You have two functions, so you're going to have two terms. Each one has both of those functions, but one of them you're taking the derivative of in each product. Okay? So this first one, we have F and G, but we're taking the derivative of G. For the second one, we're adding together with it. We have F and G, but now we're taking the derivative of F. Okay? So as long as you keep in mind, you've got to have both of them multiplied together, but one of them is differentiated in each pair. This is pretty easy to remember. Okay? So let's actually look at how to use this with a function like 3x minus 2x squared times 5 plus 4x. Now, how could we take the derivative of this? What? The power rule, okay, but what would we have to do first? We'd have to FOIL it together, okay? We'd have to FOIL it together in order to use the power rule. And that would work, and if you want to do it that way, go for it, okay? But this is a nice simpler one to start looking at the product rule with. As we're examining our function here, h of x, we can see it as this 3x minus 2x squared being like the first function there, f of x. And the second function, 5 plus 4x, would be our g of x. That's the second function, okay? So we've identified those two functions. Now we're going to take and find the derivative of f of x. So what is that in this case? Terry? Very good. 3 minus 4x. That's the derivative of f. We also, in our formula, need the derivative of the second function, and what is that? That's 4. Okay? So notice I am taking the derivative of each part, but I can't just multiply those together and say it's the derivative of the function. I have to use this power rule. So let's look at using the power rule. H of x is going to be f times g prime. By the way, sometimes we leave out the of x's just for ease of writing. F times g prime plus g times f prime. Alright, so now it's just a matter of filling that in. H prime of x is f, which is 3x minus 2x squared, times g prime. Well, g prime we got over here, that's 4. Then we add to that the original g, which is 5 plus 4x, times f prime. Well, f prime we figured out over here as well. It's 3 minus 4x. So we fill that into our formula, and at this point all we need to do is then to simplify. Okay, so h prime of x is 12x minus 8x squared. We FOIL the second half there. 15 minus 20x plus 12x minus 16x squared. And finally we get that derivative equal to a negative 24x squared minus 8x, minus plus 4x plus 15. Okay, so there's our derivative. Just to double check ourselves, if I had FOILed this together, I would have gotten a negative 8x cubed plus 12 minus 10, so that would be a plus 2x squared. And then I would have had a plus 15x. And if I took the derivative of that, notice I would have gotten the same thing. Okay? Now, which of these is easier? Probably FOILing and using the power rule. Okay? So if you see one that's easy to simplify, go ahead and do it. Alright? But there are going to be ones that we can't just simplify and use our power rule all the time. Like this next one here. Okay, this next one we have y equals x times the sine of x. Okay, now what is f of x in this case? It's x, that's right, okay? It's x, so f prime of x is? One. There we go. The derivative of x is 1. Wake up. Okay? The derivative of x is 1. So then g of x is what? Sine of x. Well, the g is sine. G prime of x is cosine x. Okay? So now, again, we can use the product rule to find, in this case, dy dx. Fg prime, so f is x, g prime is cosine x, plus g times f prime. So sine of x times 1. And of course, the 1 is irrelevant because you're just multiplying by 1. So our derivative is simply that, once we simplify the times 1. Okay? Not too bad, right? Not too bad. Now, another thing that we're going to see here when we look at our various rules is that certain rules will be used within the context of another problem. Alright? So for example, here we have y equals 2x cosine x minus 2 sine of x. So we have multiple terms, so we're going to have to take the derivative of each one separately. However, do I need to use the product rule here with the minus 2 sine of x? No. Could you? Yes. But one of your functions, if you're going to view it that way, would be the minus 2. That's a constant. What's the derivative of a constant? 0. Okay? So, you don't need to use the product rule on the second half. We're just going to take the derivative of the first half using the product rule. And then I know my dy dx is going to equal whatever I get there minus 2 times, what's the derivative of sine? Cosine. Alright, so I know it's going to be something minus 2 cosine of x. So I'm going to come over here, and I've got to actually figure out what is the derivative of 2x cosine x. Okay? So, like our previous one, I'm going to identify f of x and g of x. F of x is our 2x, g of x is the cosine of x. Okay? What is the derivative of 2x?
2.
Come on, guys. 2. And what is the derivative of g of x?
Sine of x.
Minus sine of x. The negative sine of x. And now we can substitute that into our product rule, okay? So we have g cosine x times f prime, which is 2. Then we have f, which is 2x. We're adding here. Times g prime, so that's a negative sine x. So I'm going to put the negative in front here. So now I can come back over here, and I know that it is 2 cosine x minus 2x sine of x. Okay? So, that part all came from the 2x cosine of x. Alright? The nice thing with this one is we have a 2 cosine minus 2 cosine, and that gives us a final answer, dy dx, equal to a negative 2x sine of x. Okay? Again, not too bad. You just have to be careful to plug it in properly and to see each part separately. Okay? Now, the cool thing here is that this also can be extended to account for things with 3 things multiplied. Alright? Now, I told you up here that the product rule is just the product of the 2 functions where one is differentiated plus the product of the 2 where the other one is differentiated. If you kind of think of it in those terms, we can look down here at the extended product rule and deal with 3 terms. Notice each of these 3 things that end up being added together have f, g, and h in them. It's just each one has a different one differentiated, and the other 2 are the original functions. Okay? So for example, if I have x squared sine of x cosine of x, I'm going to view the x squared as my f of x. I'll view the sine of x as the g of x, and I'll look at cosine of x as the h of x. Okay? Now, what is f prime of x here? 2x. What is g prime of x? Cosine of x. What's the derivative of cosine? H prime of x. Negative sine of x. Okay? So now when we are taking the derivative of this whole product, dy dx is going to equal you put the two original functions, okay, along with one derivative. So if I used the 2x first, then the rest of this would be times sine x times cosine x. Plus, I'm going to use the original f of x now, but now I'm going to put in the derivative of the g of x, which is cosine x. And then I have another cosine x, which was my h of x. And then finally, I have the original f of x, the original g of x, and then I have the derivative of h of x. So that's a negative sine of x. And you can simplify it a little bit here. dy dx is 2x sine x cosine x plus x squared cosine squared minus x squared sine squared. And that is the derivative using the extended product rule. Okay? Now, if you wanted to derive this yourself, you could. It's really not that hard of a derivation. You would just have to see it as f times g of x h of x. Use the product rule once, but then when you had to take the derivative of that g of x times h of x, you'd have to do the product rule with that. So it's kind of the product rule within the product rule, and it comes out to this pattern. Somebody asked if this extended out to, 4 things multiplied or 5 things multiplied. I actually haven't tried it. We could try. I'm not sure if it would work every time or not. We'd have to try it out. Yes?
So the derivative of positive sine x is positive cosine, and then when it's a positive cosine, it's negative sine x?
Yes.
Okay.
Yes. And actually, there's kind of an easy way to remember this. I haven't shown it to you yet, but if you do SC, negative S, negative C, as you go down, this is going to be the derivatives. So the derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. The derivative of negative cosine takes us back up to sine, and it's kind of cyclical that way. This will be helpful especially later too when we do integrals, because the integrals go the other way. Okay? So, we'll look at that when we get there. Alright, so last thing here I want to look at is our quotient rule. Okay? We've done multiplication. Now we're going to have to do division. Okay? So how do we take the derivative of a function divided by another function? And it's g times f prime of x minus f of x times g prime of x, all over g of x squared. Okay? Yes?
This one's not interchangeable on the top. Right?
No, because it's subtraction. You have to have it in the same order. Now, there is kind of a catchy way of remembering this. If you think of g, g is always on the bottom. It's the denominator. It's the low one. F is the numerator. It's the high one. You could say low d high minus high d low all over the low squared. Low d high minus high d low over low squared. Okay? It's kind of a silly way to remember it, but it helps, okay? Or other people use bottom and top, okay? Bottom d top minus top d bottom over the bottom squared. Okay? It's kind of a tongue twister, but low d high minus high d low over low squared. So again though, it's the same process, just a different formula. You identify your f and your g. So in this case, f is in the numerator. Okay, that's f of x. And g of x is in the denominator. So f prime of x would equal what in this case? What's the derivative of 5x minus 2? Yeah, just 5. And the derivative of x squared plus 1? Yeah, 2x. So g prime of x equals 2x. Okay, not too bad. So then we have to use our formula. Okay, our formula for dy dx is low d high minus high d low all over low squared. Don't forget to square the denominator, okay? It's low squared. And then it's just a matter of simplifying. You simplify that numerator. We've got a 5x squared minus 10x squared, so that's a negative 5x squared. Plus 4x, sorry, plus 4x plus 5 all over x squared plus 1 squared. And that's our final answer. Okay? You can try to factor the numerator. This one is, whether it factors or not, it's not going to give us anything that will cancel with something on the denominator. So we could just stop there. Okay? All right, one last one here. Notice in this case, we have this 3 minus 1 over x. How could I rewrite that? Because we don't know what the derivative of 1 over x is, but how could we write that? Yeah, 3 minus x and negative 1 over x plus 5. Okay? So again, we do our f prime for the numerator, derivative of the numerator. We do our g prime as the derivative of the denominator. And what is f prime in this case? Yeah, it'd be a positive x to the negative 2. Okay, I would not switch that back to a fraction right now. I'd wait till after I simplify some, once it's in the formula. What's g prime? It's 1. Okay? So, dy dx, again, we have low d high minus high d low over low squared. Okay? So we simplify. When I distribute that x to the negative second power into the x, I get x to negative 1 plus 5x to the negative 2 minus 3 plus x to the negative 1 all over x plus 5 squared. And now that we're at the end, let's go ahead and simplify those negative exponents. We have 2 x to the negative 1, so that's going to be 2 over x plus 5 over x squared minus 3 all over an x plus 5 squared. Okay? And that's our quotient rule. Yes?
You want me to simplify
No, not at this point. We could multiply the numerator and denominator each by x squared and get rid of the complex fraction, but we'll just stop there for now.
Section, is it 2 over, because it was 2x minus 1?
Yeah, there were 2 of the x to the negative 1s there. We put them together. All right, that's it.